My name is Mary Conquest. I'm your host for Safety Labs, the podcast where we explore the human side of safety to support safety professionals. We move past regulations and reportables to talk about the core skills of safety leadership: empathy, influence, trust, rapport. In other words, the soft skills that help you do the hard stuff. This podcast is created by Safety Products Global, the world's leading manufacturer of safety knives. Through our trusted brands, Clever, Slice, and PHC, we empower companies to prevent injuries by providing safer cutting tools for every material and application. Hi there. Welcome to Safety Labs. We all know what happens when things go wrong, and many of our guests talk about the benefits of studying what went right or learning from normal work. Today's guest looks at these problems with the wider lens of a systems engineer. We're going to talk about different methods that help expose hidden dangers in complex systems. And I'm hoping these tools will help you in your work, regardless of the complexity of the systems you work with. Simon Whiteley partners with organizations and professionals responsible for safety in complex, high-stakes systems, where the cost of missing something is measured in lives, catastrophic loss, mission failure, or regulatory exposure. He uses advanced methods to help uncover issues that conventional approaches are not equipped to deal with. Simon specializes in system safety engineering, accident analysis, and advanced applied methods in complex domains such as space mission safety, aerospace, and defense. His work exposes dangerous successes, that is, catastrophic losses that occurred not because a component failed, but because the system behaved exactly as designed. In other words, the danger hiding in what went right. Simon joins us from Salisbury, England. Welcome.
Hello. Thank you for the warm welcome.
What is system safety engineering, and how does that differ from traditional approaches to occupational safety?
Well, system safety engineering is a discipline of applying engineering principles to the subject of safety. And it originates primarily in the US in the 50s and 60s from the space program, and particularly the development of ballistic missiles. And they essentially developed safety analysis methods such as fault tree analysis and failure modes and effects analysis to essentially solve the problems of that era. You know, if you've got a quite a spicy weapon on top of a missile, you don't want the thing to go off at the wrong time. And likewise, you don't want your missile to crash. So they were trying to solve problems in in that era from a failure focused mindset. So what are the failures that will lead to the loss of the craft or an explosion, and how can they deal with it? And in terms of occupational health and safety, that's kind of outside of my domain a little bit. I suppose from a layperson's perspective, I could say that system safety engineering is more about worrying about the factory blowing up versus some individuals getting workplace injuries and ill health. But there are some parallels. There is some crossover.
Yeah, I would say it's definitely there's a Venn diagram there. Does safety system engineering work better in some industries or workplaces than others? Like, it's applied to certain industries. Is that just an accident of history, or is there a reason for that? It just doesn't work elsewhere.
Yeah, so system safety engineering as a discipline, as I mentioned, it originated trying to solve problems with really big, expensive, horrific hazards. So, like I said, with ballistic missiles and nuclear weapons, and then over time in aerospace and defense. So, trying to develop aircraft that were safer, that were not going to crash as much. I mean, at the end of the Second World War, some of the weapons that were coming out of that period of, rapid innovation were really, really complex, like more complex than anything in human history. And an example which the human factors community use a lot is the Boeing B-17 bomber. So they had a lot of issues with aircraft crashes after takeoff because the pilots were, either, if I remember correctly, it was either lifting the landing gear up and down at the wrong time, or it was to do with selecting the flaps. And if you do either of those in a certain context, it can be quite dangerous. And when they looked at the cockpit interface on that aircraft, they realized that they could have probably done it a bit better and stopped so many accidents. So it's really the discipline of applying engineering principles to the problem of safety. Sorry, what was the rest of the question? I missed that.
That was all. Just like, does it work better in some industries
Oh,
or
yes. Yeah,
workplaces than
sorry. Yeah.
others?
So
Are there
it originates in complex systems, expensive systems like aerospace and defense. And then over time, some of those principles have leaked out into other industries, such as the nuclear industry, automotive industry, the space industry. But it's managed to stay in those kind of transportation, complex technologies industries. It really hasn't found, as far as I've seen, much impact in, for example, healthcare, where I believe it could have a really, really significant impact if it was considered and implemented in an appropriate way.
I want to go back to something I mentioned in the introduction, the term dangerous success. Can you explain what do you mean by a dangerous success?
Okay, so typical safety analyses focus on what went wrong. So if a failure occurs and that leads to an accident, then to prevent future accidents, it makes sense to go and find out what the failures are that we're concerned about, and then either eliminate them completely, or if we can't eliminate them, design the system, the operation in a way that we can either accept them or we can respond and recover from them. And an obvious example of that from an aerospace is if you have a passenger aircraft with a propulsion system, an engine, and you lose that engine for whatever reason, it's probably a good idea to have another engine or more to deal with that situation. Now, the challenge with that and the methods that are used to find those dangerous failures is there are so many different combinations, so much detail that you have to look through to find those dangerous failures. But then on top of that, you've got what I call dangerous successes. So this is where the system has behaved as you've designed it, and that leads to an accident, that leads to a loss. Now, you could argue that on one hand, the design was flawed, it was faulty, the designers failed, the designers made a human error, and so that's why the accident occurred. But if you look at it through a more sort of broader lens and start thinking about, well, what is it about what went right that led to this accident? How can we actually engineer that or change that so that it doesn't result in an accident in the future? Because ultimately, it's done what we intended it to do. But what we didn't do is anticipate that that specific situation with a specific context will lead to an accident. So, using the aerospace example again, if you're flying your passenger jet on holiday and the pilots are coming into a hot and high airport, and at the top of the descent, they have to slow down, so they pull the throttles back to slow the engines down. When you're operating in hot and high conditions where the air is thinner, less dense, the engines take longer to slow down. And on the engines, most modern engines, they have what's called a thrust control. Sorry, no, it's called a TCM. But essentially, what it does is it monitors the performance of the engine. And if the engine is not where it thinks it should be, it will decide, hang on, the engine is misbehaving. In this case, it's not going as slow as we want it to, it's still going too fast. So, this monitoring system, this safety mechanism, essentially thinks the engine is running away, and so it commands it to shut down. Now, of course, if you've got both engines with a safety mechanism on it, and they both believe that the engines are misbehaving at the same time, they will shut their engines down. And so you'll end up with a situation where your engines have shut down, not because of a failure, but because of a design of the system, a design of the safety feature. And so the methods that I'll talk about in a little while, they're specifically designed to find those kind of circumstances and help us to either eliminate them or to respond and recover to them.
So it's a little bit of the science of unintended consequences.
Yes, yeah. Well, they want the engines to shut down in certain circumstances. Could it Because it could be really dangerous if the engine is running away. But if the engine's not running away, but the safety protection mechanism thinks that it is, that's the sort of situation we need to deal with to engineer out.
So when we spoke last time, you talked about there are different models like Swiss cheese, dominoes, bow tie that are kind of broadly used. What problems would you, first of all, I'm kind of lumping them into a group. I'm not sure if that's an accurate thing or not, but you can tell me in a moment. But what problems do they help understand and what are their limitations?
Okay, so broadly, there are some easily recognizable accident causality models. One of those is the Heinrich domino models. You've got a series of dominoes, a series of events that have a knock-on effect to the next event, and then eventually they result in an accident. Then we've got Professor James Reason's Swiss cheese model, which looks at the world through the lens of you've got some people or assets you want to protect, and then you've got some hazards or things that you're concerned about, things that are dangerous. And to protect them, you put some barriers in place. And in principle, the more barriers you've got between the people you want to look after and the hazards, the safer the system. But of course, there are going to be holes in those barriers. There are going to be holes in that Swiss cheese. And if those holes line up, then an accident might result. Now, those two models are just examples of what's called a linear accident causality model. So they look at safety through the lens of cause and effect in a linear chain, and it's a natural way of thinking. Human beings have this natural accident causality model baked into their brains. If you see the glint of some teeth in a bush just off to the side, your brain's going to detect that, and it's going to conclude that that is possibly a predator. So maybe we need to run away. And so it's a normal way of thinking. This is how everybody thinks. But there is another accident causality model, and that is where we think about accidents as being due to inadequate control. So if we have a process, or if we have some people we want to protect from some hazards, if we don't control that situation, if we don't control the hazards or the people in proximity to it, if we don't control it adequately, then an accident will result. So what we're doing is we're sort of changing our emphasis from looking at events and chains of events and failures. We're looking at the concept of control, and that empowers us to be able to find more causes of accidents, including those subtle ones that are not due to failures. They're due to the way the thing is designed, the way the thing operates.
Okay. So I'm going to ask you more about that and some of the methods that you find useful, and hopefully our listeners will find helpful. But first, we're going to hear from the company behind the podcast. So, in warehouse, distribution, and retail environments, cutting tools can take a beating. Flimsy blades won't suffice. Traditional knife designs also increase the risk of injuries and damaged goods, which is why Clever Cutter built the Clever Eco Exchange XD, which this design, the blade is in here, protects fingers and merchandise. The blade head is engineered to be 50% stronger and last 4 times longer than similar cutters. There's an integrated tape splitter at the top here, which saves the blade for cutting. It cuts up to 1 mile of corrugate, and when it's time, you only have to replace the blade head. It comes out and you can replace it with a new one. If you'd like to learn more about which tools will work for your materials, you can request free samples at safetylabspodcast.com/samples. And now back to our podcast. Okay, so let's start with some principles, which there's an acronym, STAMP. So can you explain to me what STAMP is?
Sure. So STAMP is an acronym, a label that refers to a set of ideas and principles that essentially reframe safety as an inadequate control problem, as opposed to a failure problem, which is the more traditional accident causality models. And the acronym itself, it refers to Systems Theoretic Accident Model, and the P stands for processes. So the acronym refers to two things: the underlying accident causality model and ideas, and then some processes built on it that use those ideas to either do safety engineering, so anticipate potential hazards and causes of hazards, or if you're doing an investigation, to find out, what has actually caused the hazard so you can prevent it in the future.
So how does it work? What is its relationship with probability? How does it? I guess you sort of talked about how it's different from previous linear approaches. So why is this important to understand or learn about?
Okay, well, as I mentioned before, it allows you to look at your problem, your system, your operation, whatever it is, through the lens of a control structure model or a control loop. So you essentially look at what is the process that where harm can occur, where hazards exist. How is that hazard, how is that harm controlled? What does that structure look like? So you essentially make your system explicit, and then you can explore, well, what is it about this system, this structure, that can contribute to an accident or a loss. So, if we're talking about, I'm trying to think of some good examples. There's so many examples, but if we're talking about a chemical plant, one of the things that we're trying to avoid is the release of these dangerous chemicals. And essentially, we create a model of the control structure for that particular hazard to understand what could contribute to releasing hazardous chemicals. And then we can set requirements for it. And then when the plant has been designed, we can do an audit and check to see if those requirements have been met. And then, of course, if there's an accident, we essentially establish, well, what was the control structure involved in that situation, and how was it deficient? How was it inadequate to prevent this hazard from being released? And then, of course, we can make recommendations. And that sort of highlights and I'm going to be a little bit facetious here, so please, I apologize. But when we talk about root cause analysis in the context of an investigation post accident, often it's about focusing on, well, what is the root cause or root causes that led to this outcome? And essentially, when we look at an accident through the lens of STAMP and use the method CAST based upon it, what we're actually looking for are the reasons why the control structure was inadequate. Because it could be that everybody worked as designed, everybody did what they were supposed to do. It's just they weren't given the right equipment or the right training to do what they needed to do, and it's not the fault of the individuals involved in that situation. It's down to the next layer up in the control structure, the next layer in the hierarchy. So leadership. So why might leadership not provide that resource? And so you can then look at the next layer in the hierarchy, all the way up to, the law of the land, governmental, and even beyond if you want to go that far. So yeah, and so STAMP is all about what is the control structure, what is the controller to control these hazards. And as I mentioned before, because we now focus on reasons for inadequate control, and that can include failures, but also dangerous successes, what went right. But also because the underlying principle is that complex systems, especially organized systems, which human organizations and technical systems are, at that sort of scale, probability and likelihood estimations, they don't work at that level. The probability of all of these different moving parts achieving a certain state on a particular day, it appears to be so unlikely that you just wouldn't even bother to try and mitigate certain situations. But because STAMP doesn't include the concept of probability in it, it's essentially a worst case analysis method. You start from the outset, what are the losses that our stakeholders find unacceptable? We don't want to hurt or kill people. We don't want to blow our own factory up. We don't want to upset our customers or the regulator. So these are the losses that the stakeholders are concerned with. And so what are the hazards associated with that? And by extension, what must the control structure be to be able to mitigate, eliminate those hazards? And if we can't eliminate them, what are the response and recovery methods we can put in place? So it really opens up your scope of what the art of the possible is. And because you're essentially released from having to, how can I be polite, convince yourself that probabilities are smaller than they actually are, or that the numbers actually mean anything, because you're released from that and you don't have to spend time, resources, or stress thinking about it, you can focus on what actually matters. And that's making sure that adequate control is possible. And if it's not possible, that you can do some kind of response and recovery to it. And of course, that makes a lot of organizations uncomfortable, especially if they are required by the regulator to use probabilistic based safety analyses and safety arguments. And so, of course, there's a bit of an obstacle, a bit of a barrier to those stakeholders wanting to take on STAMP, STPA, or CAST. Because if they're asked by the regulator, hey, we need a probabilistic safety analysis with a number on it, and you're telling us you're going to use STPA that doesn't have probabilistic analysis as part of it, of course, they're going to be a bit reluctant and a bit sort of like, well, hang on, you still need to do the probabilistic work. But if you're going to do STPA as well, you should do it in parallel so you get the best from both worlds.
So it sounds like it's a design approach where you can either look before or after an event. And I was thinking of the case that you mentioned with the airplanes and the high and dry airports being different. It sounds like you have to account for context as well.
Yes, context is the key. Absolutely. Well, just picking on your advertisement for the knife, you could, if you think about it through the traditional lens of what is a hazard, typically they say it's anything that has the potential to cause harm. And so by that definition, you could say, well, that knife has the potential to cause harm. But that's a bit of a meaningless kind of definition. It's not helpful, especially in occupational health and safety. It's not really helpful. So in STAMP, there is a different, more specific definition of hazard that essentially allows you to think about the system state that will, in combination with a certain environmental state, lead to a loss. And so you start thinking about system states and events instead of necessarily just physical interactions. And so in the case of the knife, the context of the knife is if it's on its own in a locked room, it's not really presenting harm to anybody. So the next question becomes, well, what if you unlock the room? What if you let children in there? Well, yes, of course, there's always a potential that some negative outcome might occur. But let's look at it through the lens of control. How do we control the knife? Or more broadly, how do we control other people's interactions with the knife? And so it allows you to sort of think more broadly, reformulate, well, what is the hazard we can actually control? And if you're a knife operator using this analogy, you own the office building where this knife is present, then of course you have some level of control and responsibility over access to that knife or its existence in the first place. But if you were the designer of a knife, how would you approach that particular hazard? Well, you might say, here's some instructions to a knife purchaser. Please don't let children get near it. Well, that's one way to mitigate it. But what are the other things you could do from a design perspective? And so in your little presentation there, they've actually thought about, well, how do we control access to the blade? And so they've designed it. They've designed the controls into that hazard. Yeah, so it allows you to think about things very much from a design perspective and an operations perspective, but also from a response and recovery perspective. It allows you to think much more broadly about what you define as a hazard. And I challenge everybody watching this podcast to go and look at their risk list, their hazard log, have a look at that definition of a hazard, go and look for the definition of hazard in STAMP and just have a think. How does your definition compare to the definition in STAMP? And you'll start to see that it will force you to start thinking more broadly about, well, what is the thing we need to control? How do we control it? How might we control it if things go wrong or we need to respond and recover?
Okay, so I'm going to get into the methods in just a
Yeah,
second, but
sure.
I'm
Sorry.
curious. You mentioned, well, you mentioned the objection of regulatory
Yes, probabilistic.
requirements
Yeah.
and probability. Are there any other common objections or maybe misunderstandings of this kind of stamp approach? And if so, how would you address them?
Sure. So there's a couple of key ones, and at least one of the ones I'm about to say might not make sense to those that are not familiar with how STAMP and the methods based on it work. So I'll try and refer to those. So the first is about when you do, for example, an STPA hazard analysis, which we'll talk about. Part of that process is essentially examining your control structure for what are called unsafe control actions. So these are the situations that if they occur for whatever reason, failure or success, it doesn't matter. If they occur with a specific context, then that will lead to a hazard or it'll lead to a loss and something bad will happen. Now, when you're exploring those types of control action, there are a series of scenarios, a series of types of unsafe control action. So the first one could be if the control action is not provided. So if you're driving your car down the road and you do not press the brake when there's somebody a pedestrian in the road in front of you, will that lead to an accident or a loss? Well, the logical answer is yes, you'll hit the pedestrian and something bad might happen. If you provide the control action, the brake command, in that same context, will that also lead to a loss? Well, in that circumstance, you're pressing the brake, so you're going to stop moving and you won't drive over the person. So that's actually a safe control action. We want our car to do that when we press the brake. But what about a situation where you're driving along merrily, a different context, and there's nobody in front of you? but there is somebody behind you following in a car too close behind. If you provide that exact same control action in that different context, then logically that will be an unsafe control action. And when we're doing that activity as part of STPA, you're essentially using some tables, tabular form, to do the analysis. So you've got control action not provided, provided, and then you can start thinking about the timing of those control actions, if they were too early or too late, maybe even the duration, too long or too short, or if if there is a particular sequence that needs to be followed of these control actions, such as ready, aim, fire. If you do ready, aim, fire in the wrong sequence, perhaps some bad things will happen. And so when you're doing that activity, it is in a table. You can do it in a table if you like. And so people who are not that experienced with STPA, when they first see those tables, they think, oh, hang on a minute, that looks just like functional hazard assessment, or it looks like FMEA. So it's not much different from that. And so that's the first thing. The second thing is, picking up on failure modes and effects analysis and the topic of conversation about probability. So when you do a failure modes and effects analysis, you essentially drive out as many different failure modes as you can. And then if you want to get really advanced, you can start thinking about the probability of those failure modes, maybe even the severity of the outcome, and maybe even add a risk number, a detectability number if you want. So you can start playing tunes in spreadsheets with lots of numbers, and it looks really exciting. But when you take a step back and say, well, the probability of these particular scenarios occurring with these other contexts, the maths gets really complex and really unrepresentative very quickly. So why are we wasting our time doing that? But that's a separate conversation. So they see the tables in STPA, they know the tables in FMEA, and then they start trying to put probabilities into the STPA unsafe control action analysis tables to try and give them a warm feeling that this particular scenario will be low probability or whatever it is. And it just doesn't work. It's not an appropriate thing to do for complex systems. And then the third aspect is to do with building the control structure models. So when you see them, they're essentially just boxes with arrows in a hierarchy, and it just looks like any diagram with boxes and arrows. But there is a language to it. There is a structure to it, a general sort of flow and format. And so if you don't necessarily know what you're looking at and you don't appreciate what the arrows mean and how it fits together, it can just look like a reliability block diagram or some other hazard analysis, such as AxiMap. It doesn't look like FRAM because they're different symbols, but when you see a FRAM, you know that that's a FRAM. When you see a stamp control structure model, unless you know what you're looking at, it can just look like a diagram with boxes and arrows. So in that context, it can look really simple. It's just boxes and arrows. But when you really develop these models, there's a lot of potential subtlety that beginners might not appreciate, if that makes sense.
Yeah, it sounds like it's just mistaking the artifact for the process, essentially.
Yeah, absolutely. Yeah. It's the thought process. When you're building those models, it is leading you through a creative thought process. And the more stakeholders you have involved in that activity, the better it actually is. It's teamwork. Teamwork is fantastic.
Okay, so let's get into the details of. Let's start with the cast method. How does that? What's it for? How does it work? Tell us all about it.
Okay. So CAST itself is an acronym for Causal Analysis Using Systems Theory, or using STAMP, depending on what literature you read from what period of time it was written. And essentially what it is, it's using the principles of STAMP and the ideas within it to support an accident analysis. I'm being very sort of specific about saying accident analysis because there is a bit of for beginners, often they mistake accident investigation for the analysis that's done as part of an investigation. So CAST is an analysis method that you would use as part of an investigation. And essentially what it involves, and the way I teach it, which is slightly different to how it's discussed in the various handbooks and literature published by MIT, etc., is there's broadly three phases. The first phase is a foundation phase. So this is where we set the scene of, well, what is the thing that we are going to analyze? What is the situation we're going to investigate? What is the system? And then, of course, what are the hazards involved in this accident or incident that we're investigating? And that sounds like a really easy. Oh well, of course we know what the hazard is, but it depends what sort of accident you're dealing with. If you're dealing with something like the MH370 aircraft that disappeared and nobody knows where it is, you don't really have anything to sort of start with. So that's a bit of a challenge. And so, as part of the foundation phase, we define what our losses are, we define what our hazards are, and then we define what are called high-level safety constraints. And these are the things that the overall control structure in all of its glory is supposed to either prevent, so eliminate or avoid a hazard. And if we can't do that, then we need to be able to mitigate it or manage it. And then we need to be able to provide some kind of response and recovery. So this is setting high-level requirements. And then the investigation itself and developing the control structure model starts from that position. What are the hazards involved in this accident? What is the control structure associated with that? And then what is the actual control structure involved in this real accident? And this allows you to make explicit work as imagined, what's documented in all the procedures and everybody's training versus what's actually happened, what actually has been done. And so you could then see where the gaps are between the two elements. And when you build your control structure model, you essentially start from the physical world. What is the control process? What are the bits of equipment involved, the mitigations, the controls? Who are the people? Who are the controllers involved in that? Is there any kind of software or AI or some other kind of controllers, including humans? What is the human-machine interface between that process and the humans involved? And then as you add detail to the model and make it, much more detailed, you can start to see what the layers in the hierarchy are. So who is involved with controlling the people in this involved in this control process? Who are the leadership? Who are the regulators? Are there any other important stakeholders we need to consider? And so as you're building that model, you can start doing that from a very simple perspective of just a couple of boxes with some arrows. And even at that level of detail, it can help you to ask some very powerful questions as part of your investigation. I mean, I use that method when I'm doing interviews and as part of investigations. When I interview somebody, I let them tell me in their words what happened, how they experienced whatever it was. And then once I've got that information out of them, I can start to think, well, whereabouts do they sit in this control structure model that I create in my mind? And what type of questions I need to ask them, such as, what control actions did they provide? What did they believe? What was their mental model? What decisions did they make? What feedback did they receive? Did they receive feedback? So it helps you to structure the questions as part of an investigation. And then the third phase, I suppose you could say it's a final phase, it's kind of sequential, is the analysis phase. Now, the analysis phase for CAST has three parts. The first is the physical process analysis. And this is what we typically do as part of any investigation we do today. It's not special as part of CAST, it's what we already do. And so, what is it about this physical process? If somebody has been injured by the knife that you showed earlier on, is it that there were some mechanical issues with the knife? Did the guard break down or something like that? So, we're very much focused on the physical process. And then the second part of the analysis is what's called controller analysis. So this is where we examine the controllers in the control structure to understand what control actions did they provide? Why did it make sense for them to behave the way that they did? And so we're looking at both failures and success. And we're taking, we're being really careful not to suffer with hindsight bias. So for example, and this is a bit of a ridiculous example, but if you're familiar with the Chernobyl disaster in 1986, there is a TV show that's fantastic. You've got to watch it if you've not seen it. But essentially, there's a scene in that where one of the control room operators goes to press the emergency stop button. It's not actually a stop button; it's a twist key. But anyway, so they had a belief that they need to press the emergency stop button. So they go and press the emergency stop button, and then boom, the reactor explodes. It would be entirely appropriate to say that that individual, that controller, provided an unsafe control action. And the reason for that is because with hindsight, we know that pressing that emergency stop button in that context will blow up the facility. But that individual logically didn't know that. And so their mental model was, I need to follow the process. I need to do what I'm told to do, which is to press the emergency stop. And they logically had the belief that it would save the day. Had they known that pressing the button would blow the reactor up, they probably wouldn't have pressed it. But if we do a traditional investigation, would we blame them and say, hey, well, you didn't follow procedure, you didn't press the emergency stop button? And they say, well, we thought it would blow up the reactor, so that's why we didn't do it. I know that's an alternative reality, but I'm just trying to help the viewers understand that when you use these methods, it allows you to avoid it helps you to avoid hindsight bias, and it helps you to be very respectful of those involved in an accident. Because most people come to work to do a good job. They don't come to work to hurt themselves or hurt others. And so when we interview them and when we do our investigation, do our analysis and write our reports, we have to be respectful of that and mindful of hindsight bias. And then the last part of the cast accident analysis is called the control structure analysis. And this is where we explore the control structure to understand what contributions it has to the accident, to inadequate control. And an example of that could be literally missing feedback. This is often a common cause in accidents where a controller has done something and that has resulted in an accident. They've provided a contributory control action. And then when you do the investigation and look at the structure that they are part of, we find that they have missing feedback. So they did what they thought was the right thing to do. They didn't fail, but they didn't have feedback. And so it allows us to make those kind of issues explicit. And of course, control structures and controllers and physical process analysis, when you mix that all together, you have such a powerful analysis tool that you can go really, really far. And of course, that can be quite threatening. And what I mean by that is, and you might have seen this from my recent live streams on LinkedIn about the Boeing Starliner accidents. When you start using these methods, because you can start looking into the higher layers of an organization, shine a spotlight on these things. There are certain people in those organizations that might not be used to that, might not be receptive of it, especially if they're going to be held accountable for decisions that they've made. And of course, again, we have to have an open mind that people might behave in a certain way that with hindsight it looks bad, but when you go back in time and look at the real context, they may have been behaving in a way that was entirely appropriate for their context. And it's only when you shine a spotlight on them that other things can be found. So that's essentially CAST. So 3 phases, 3 parts to the analysis phase.
So that's interesting because one of the questions I had in my mind was, when you talk about control and control structures, some of our other guests have talked about essentially like culture, unwritten ground rules, things like, for example, there was a cruise ship accident in, I think, 2012, the Costa Concordia, and there was a competing pressure where there were certain norms in the industry. It was quite normal to do a sort of a sail by, I think it's called. And there are these competing pressures of safety and commercial pressures to wow the customers, I guess. I don't know, the cruisers, the people on the boat, which led to an accident. So I guess I was thinking, like, when you talk about control structures, initially it sounds like there's not much of the human in that. There's not much of the culture, the unspoken, that sort of thing. But you did actually mention quite a few areas. Well, like, why did that make sense to you? Well, it did because this is the industry norm, or whatever. So that's interesting.
Yeah, so this is one of the slight challenges with the adoption of STAMP, STPA, and CAST, is the languages of control engineering and systems engineering. So we talk about controllers, we talk about control structures and actuators and sensors and feedback and control actions. And when you go into an organization that is more operations focused, more people and softer skills focused, that language can strike the wrong chord. That, like in healthcare, they really don't like the word control. Actually, in some circumstances, they have a view that, well, you can't control anything; it's chaos. we do the best we can in the storm. So how can you say we control these things? And so there is some. It sounds, from an engineering perspective, it's like we've got a good vocabulary that's nice and clear that you can apply to any system in any domain. So it's domain agnostic. It's hierarchical level in an organization agnostic. So someone who is talking stamp language in physical processes can also have the same conversation with people in higher levels in the organization. So it's a universal systems language. But if you're in a certain industry or certain part of that structure, that language can sound very coarse and potentially inappropriate. So there's always opportunities for misunderstanding. And so it's important that when you're teaching people or working with people, you're always listening for that change in tone or whether they interpret it in a certain way. But fundamentally, STAMP covers, humans, technical, organizational, regulatory, the natural, all of it. It brings it all together in that control structure. But the label control structure does sometimes give the wrong connotation. And so it's good to have that conversation. I'm glad you brought that out. I hope that's helping the audience, actually. Thank you.
Yeah, well, it occurs to me too, like when you're interviewing someone, for example, you wouldn't say, so what were you, or maybe you would, but what were your controls? I think the average person would be a little confused by what you mean by that.
Yes, they would. Yes, absolutely. So don't do that. I'm not suggesting when people, don't do that. Use the language in your head, but when you're talking to people, especially if there's something bad happen and you are interviewing them, you have to be very sensitive and respectful and talk to them in their language where they are in the control structure. And there has to be a little bit of interpretation, and we have to be careful how we interpret things. And that's why there's a difference between the language when we talk about control actions that are unsafe with a certain context. When we talk about those in STPA hazard analysis before an accident has occurred, that's where we use STPA. We refer to them as unsafe control actions, UCAs. But when we're doing an accident investigation and we're trying to understand what are the unsafe control actions that contributed to this accident, we shouldn't use that label. We should use contributory control actions. Because like I said before, the guy working in the Chernobyl control room, to refer to them pressing the emergency stop button as an unsafe control action is a ridiculous label. And some might be listening and thinking, oh, well, we're just talking about labels and language here. It's not a big deal. But trust me, when you're writing an investigation report, you have to make sure you're not suffering from hindsight bias as best you can and refer to things in a respectful and appropriate way. And so a contributory control action and an unsafe control action, they are logically and functionally identical. It's just the context within which we're talking about them, post-accident or pre-accident.
Yeah, and I think that being conscious of that too means that you'll get better information because,
Yes, yeah.
as you said, they're functionally the same,
Yeah.
but the word unsafe carries a judgment
yeah.
with it.
Oh, yeah, or judgment. Yeah, we've got to be really careful of that.
So I think if people sense that, they're not going to want to talk. But anyway, I'd like to, so we've talked about CAST.
Yes.
And we have actually talked about STPA a little bit.
Yeah,
but
a few times.
Can you explain it, I guess, more sequentially or logically or whatever? And when does it add value to your work?
Sure. So STPA, System Theoretic Process Analysis, is a hazard analysis method based on STAMP, the principles of STAMP. And so the way I teach it, it has, again, 3 phases. You'll notice they both have 3 phases because of the way I teach it to make it easier to jump between one and the other. So it's the same foundation phase, but of course, we're not looking at a smoking hole in the ground. We are, this is before an accident. We're trying to anticipate all the hazards and accidents that might occur, and we're trying to understand them to prevent them. So that's the first thing. The second phase, again, is building the control structure model. But of course, you are essentially documenting a control structure model, or you are designing one. You're saying, for these hazards, we need these controllers in this arrangement. We need these actuators. We need these sensors. So again, it's different to CAST because CAST, it already exists, whereas STPA, you're bringing it into existence. And then, of course, the third phase, the analysis phase, for STPA, it has 2 parts. The first part is control action analysis. So this is where we work around the control structure, look at each of the controllers, establish what are their control actions, and then we do some analysis. We establish, well, what are the contexts within which these control actions could be unsafe? And so if the control action is not provided, if it's provided too early or too late, if it's provided too long or too short, or if it's provided in the wrong sequence. If we have those scenarios, under what context will they be dangerous? And I'll give you another example from an automotive perspective. If you imagine you have a car that the braking system, provides a braking command and the car stops. If you think about the control action, the braking command is provided, that's, so in some context, that's what you want. In other cases, it's not. And a good example is the duration. So if you have the brake command provided too short in a certain context, that'll be dangerous. If you have the braking command provided too long, so the duration is long, then, well, hang on a minute, your car will stop. So you'll be stopped. Is that not the safe situation? Well, yeah, generally it probably is, until you find yourself stopped on a railway crossing with a train coming. And then you can't move the car off of the crossing because the braking system is on. So all of a sudden, that sounds like a bit of a silly scenario, but it happens quite a lot. A lot of modern, particularly electric cars, they have that unsafe control action designed into them. And so how do you, if you're a driver of a car, maybe a vulnerable adult, or you've got kids in the back, how do you know, what's your mental model to recover this situation? How do you know whether you should just abandon the vehicle and get kids out the back because you haven't got enough time to recover the mechanical electrical situation? And so what I'm saying is the automotive companies would get a lot of benefit from using STPA to explore those kind of example scenarios. And then the second part of the STPA analysis, and this is where it's very detailed and there's a lot of work involved, is where we look at the reasons why those unsafe control actions might occur. And the reason I emphasize the two parts is because you can do unsafe control action analysis without necessarily knowing the detail of the design of the vehicle. You could do it at an early concept stage, during someone developing a concept of operations. You don't need to know what technologies you're going to do. You don't need to know what software or what engine size or whatever, because your model is just an abstract functional model with boxes and arrows. So you focus on the control actions first. And then when you have reached a level of design maturity or information maturity, maybe you're doing a study of an existing system, you look at the control actions first, and then you pick those unsafe ones, and then you explore, well, what is it about this particular control loop that will lead to this specific unsafe control action in this context? And then you explore around that loop, you look at, well, what are the reasons the controller would behave that way? And this allows you to think about both failure modes, such as the controller lost electrical power, or you could look at success modes, where the system was operated in a hot and high condition, for example. And then you would look at the feedback path. So what is it about the feedback that this controller has that will lead it to believe it needs to provide this unsafe control action? And then again, the same with the control path, the actual actuators. Because if you imagine your braking system and you are considering the control action loss of braking, braking command not provided when pedestrian in front of you, one of the scenarios could be that your braking command went into a hydraulic actuator that had no hydraulic fluid. So of course it's not going to work. So that's your mechanical reasons for the unsafe control action. And then in terms of the controlled process, and I mentioned this with the aero engine example earlier on, your control process is the engine's generating thrust in a hot and high condition. So your pilot, they provide a control action to the engine, which is to slow down, reduce thrust. So the engine starts to slow down, but because of the hot and high condition, the engine is taking longer to slow down. And so the amount of time between the pilot pulling the throttle back and the engine slowing down exceeds the threshold for the thrust control mechanism, the safety feature. And so it detects the engine's not slowing down, and it provides a control action to shut the engine down because it believes that's the right thing to do. And so there are, when you explore the control loop, I mean, I'm not expecting beginners to do this because it takes time to get to that level of detail. And of course, you'd probably only use it in complex engineering contexts if you wanted to. But you can get to some really interesting, dangerous successes and failures that lead to these unsafe control actions. And of course, that's just one control loop, one jigsaw piece. If you start to then look at different elements of the control structure that contribute to this controller's behavior, you can unlock a whole raft of really interesting and really subtle but non-trivial causes of accidents. And that's what the power of STPA can bring. It's a number of times people have said to me, Simon, how did you find that? That's crazy. that's that's a crazy thing to find, but oh gosh, we need to do something about that. The number of oh no moments is quite interesting. It's something to measure, I think.
I have one more question about this in terms of, like, you're talking about in the design, like the conceptual level, which could then lead to, engineering specs. We must build to this specification because we've done this work, this design work. But at the conceptual level, who should be in the room for a thorough or a good STPA study? What I would think that you need more than just
Yeah, it's a team
the engineer.
sport.
Like, yeah, it's a
Well,
team sport. So
it depends. It depends how much detail you want to apply it, because you could get one person like myself who is experienced in the method, experienced in the subject matter, and we can anticipate the hazards, build some control structure models, and start finding unsafe control actions like this. When you get really good at it, it becomes second nature. And then, of course, if you need to dig into the subtle detail of the design, you can do that, but you need obviously subject matter experts that know all the details about a controller or some actuators or sensors or whatever it is for a technical design. And then when you're talking about organizational elements, that's where it gets a bit harder, because organizations and humans and teams, they're generally not hard engineered. They are generally a bit more ambiguous, a bit grey. So that's where it gets a bit challenging when you're modeling social technical systems. But the activity of attempting to build the model and ask the question, who or what is the controller? Just by starting to ask those kind of questions, it opens up, new insight and new possibilities to prevent accidents. But of course, you can also use it to do independent reviews. I was invited to team up with a well-known professor from the University of Sapienza in Rome, with the European Space Agency last year. We were invited to take part in their independent planetary protection review for the Mars sample return mission. I don't know if you know too much about the details of that, but they were going to return some samples from the surface of Mars and stick them in the Earth's atmosphere to land, and then they'd take it to a biological lab to do some testing. And so, as part of the planetary protection panel, we were invited to team and do a mini STPA project, essentially to understand what we might find using STPA, do a bit of a trial and give them some results. Long story short, we found some very interesting things that they were very excited about. And so we certainly demonstrated the value of STPA to that organization. So much so they want to start applying it to other things. But we didn't spend that much time working on it. And for me, it was my first time working on complex space systems. So it was quite interesting to see how to apply these methods to a domain I'd not previously worked in. But we were able to use the concept of a control structure to, really find some interesting things. And I can't really share what they are, but just suffice to say, it was, there's a few eyebrow raised moments in that situation. But we had access, in terms of the team structure, you have a team leader, project team leader, STPA project team leader, who is typically a facilitator. So they understand the process and how to apply it. The three phases. They understand how to identify and refine hazards. Then you have the role of a modeler, a master modeler, so somebody to create and keep control of the control structure models. And that could be the facilitator as well, if you want to have one person doing that. And then, of course, you've got the analysis phase, control action analysis, and causal scenario analysis. So you need someone to facilitate that activity. But of course, you need information from documentation and subject matter experts. So you also need somebody to keep a track of all of this information. Because when you're dealing with a complex project such as space, you can have many multi-hundred page documents with lots of information in it. And quite often you can find inconsistencies between documents. And you don't know whether they're just administrative issues with the way the documents have been written, or whether they are genuine technical issues that need to be captured and dealt with. And as I say, we found some quite interesting things. So yeah, that's the team: a leader, a facilitator, a modeler, an analyst, some subject matter experts, and then someone to capture the issues and make sure we're not missing anything.
So I can imagine it's complex when you're not even necessarily dealing with the physics of Earth at all times in the the things we take for granted. Um, if there's a listener yeah, if there's a listener who is interested in taking this kind of approach, barring, fully learning it, is there a way they could start, like a different, maybe different questions they could ask, or something that they could do that would be a good first step?
Yeah, sure. I mean, I haven't got my slides, so I can't show you any slides. But the thing I would do, in fact, actually, if you watch my live streams on the Starliner, you'll see it in there. But one of the things I do is I try to burn in everybody's brain the concept of a control loop. Because once you embrace that perspective and then start asking the questions, say, well, okay, in this situation, who or what is the control process? What is being controlled? Is it an activity? Is it a physical situation? Is it the behaviors of some other people or controllers? And then ask yourself the question, well, who or what conceptually is the controller? And how do they interact with this process? What actions and feedback do they receive? And are those actions actually control actions? Are they actually directly doing something? Or are they trying to indirectly do things? Are they trying to influence? And what does that feedback look like? And of course, what if they don't provide those control actions? If they're not provided, does that lead to an accident? If they do provide them, does that lead to an accident? And what is that context? And if you can unlock that little jigsaw piece in your mind and then just ask questions about, well, how could these control actions be unsafe? You've learnt a lot of the core benefit of what STAMP and STPA and CAST is all about. And it's only when you start want to get really advanced and detailed, you start looking at, well, why was the control structure why was that control structure in that position in the first place? Who or what leads them? Who or what empowers them? And in fact, a conversation from this morning with one of my clients is about roles and responsibilities. And so when you've identified someone or something that is a controller, ask the question, what roles and responsibilities does this controller have for this control process? Does this controller even know that they've got these responsibilities? Are they even told? And if they are told, what's the reality? Are they actually empowered and resourced to fulfill that responsibility? Because you can have all the responsibilities in the world, but if your control loop or your control structure is not equipped, then at some point there's going to be some inadequate control and an accident will result. But is it the fault of the controller? So it can really open up some fantastic questions. I'm really passionate about it, as you could probably tell. But in terms of literature and videos, you're welcome to look at some of the short videos I've got on my YouTube channel, or download the handbooks from the MIT website. They're quite insightful, but also quite long.
If you can provide me with the link after, and we can put those in the show notes, because yeah, I think that that's interesting. That Are there any other books or websites or anything that you would direct people towards, or are those sort of the main resources?
Yeah, well, in terms of sort of broad literature, so to speak, there is the official MIT, STPA, CAST, and CAST in Healthcare handbooks, which are free PDF downloads from the MIT website. I'll provide the links to that. Then there are various videos on the YouTube channel. So Dr. John Thomas, he's Professor Nancy Levison's number one at MIT. He's done some videos on YouTube. And then, of course, there are my things, if you want me to mention those and share those. Okay, so I have a YouTube channel. It's not quite at 1,000 followers yet, but we're getting close. And I've uploaded quite a few videos over the last number of years. And in fact, one of my most popular ones is a webinar with Professor Nancy Levison from 2016. So if you want to hear from the proverbial horse's mouth what STAMP is all about, I'd recommend going and watching that video. And then, of course, I do various case studies. So the one I'm doing at the moment is on the Boeing Starliner propulsion anomalies accident. So I'm looking at the technical layers and then the organizational layers that contributed to it. And we're nearly, we're 25 sessions in now. We're getting close to the end. And once I've finished that, I'm going to run a live workshop where people can get together, a free workshop, and we can talk through this case study and answer any questions that people have. And then, of course, there's my LinkedIn. So I post quite a few things on LinkedIn about STAMP, STPA, and CAS that you can have a look at.
Okay, and if our listeners want to reach out, what?
Yeah, sure. If you're ready to explore STAMP, STPA, and CAS, please visit my website, whiteley-safety.co.uk. Send me a message that says discovery, and I'll set up a call with you within 48 hours to see how I could possibly help, what questions you've got. And then, of course, if you're not quite ready for those things and you just want to learn a bit more about these methods and the principles based on it, please subscribe to my YouTube channel and connect with me on LinkedIn. It'd be fantastic to have you as part of my community.
Well, thank you. That's our show for today. Listeners, I hope it's given you some new avenues to explore in your safety work. And thanks so much for your expertise, Simon.
No, you're most welcome. I'm really passionate about it. And my aim is to essentially grow a cross-industry community of like-minded individuals that want to go from talking to taking action and getting some results, because it can be challenging. I want to try and be the mountain leader, so to speak, for STAMP, STPA, and CAS to really help people navigate the difficult terrain, because I can understand how challenging it can be, especially in a potentially challenging organisation. I've got lots of arrows in my back.
And as always, thank you to the Safety Labs team for your work behind the scenes.
Yes, thank you.
That's our show. Bye for now. This podcast is created by Safety Products Global, the world's leading manufacturer of safety knives. Through our trusted brands, Clever, Slice, and PHC, we empower companies to prevent injuries by providing safer cutting tools for every material and application. Until next time, stay safe.